Thank you very much for inviting me. It is a distinct pleasure to be visiting Pasadena, even if it's virtual. Pasadena has kind of a special meaning to me. While I've never been there personally, I grew up in a town called Pasadena that was named after Pasadena, California. However, my Pasadena is in Newfoundland and Labrador, and whoever thought this would actually make it sound more enticing has never been to Newfoundland and Labrador in winter. 4 feet of snow is not a sunny day in January. So it's a great pleasure to be here, and I'd like to spend some time today talking about stellar evolution and atmospheric properties of Cepheids and how we can try to understand these stars from a theoretical perspective. I also want to start by showing this interesting story from the Cree astronomy knowledge. The Cree are First Nations people in Canada who live across much of our nation. And if you look at these stars very carefully, you might recognize this constellation as the Little Dipper. And in the story, the wolf, the fox, and the coyote see the people struggling and decide to help them out by giving them 2 of their cubs. So the wolf says, I will give 2 of my cubs to the Cree to help them get along. The fox agrees to do the same thing, and the coyote, not wanting to feel left out or guilty, does the same thing. But in this constellation, one of my favorite Cepheids, Polaris, is the collar of the wolf. And so it's always nice to be able to see Polaris through a different lens. This talk is based on research that was conducted in Toronto. This is the Haudenosaunee word for Toronto, which is the traditional territory of the Seneca, Huron, and Mississauga Credit River. I also like to take a moment to acknowledge that Carnegie is on the ancestral lands of the Tongva and operates facilities that's on the territories of the Changwa and Quechua people. And currently being, the Tongva land is suffering from various environmental disasters. So taking a minute to acknowledge that. So I'm pretty sure, looking at this audience, I don't have to explain what a Cepheid is, but just in case, and probably remind myself because it's been a little while, Cepheids are yellow supergiant stars that are variable, pulsating objects. They pulsate radially, and we know that that pulsation connects to luminosity. The periods range from 3 days on one end and hundreds of days on, or 100 days on the other, and we could see them millions of light years away, which makes them great standard candles, of course. But this whole ability to stand candle is one of the greatest discoveries in astronomy, thanks to Henrietta Leavitt. And I have trouble looking at this plot without thinking of the story that was told by George Johnson, who wrote a biography of her, noting how Shapley tried to get a Nobel Prize for her work when a Swedish academic contacted him about nominating Henrietta Leavitt for the Nobel Prize. Unfortunately, she was deceased by that time. But this one small plot has revolutionized cosmology and stellar astrophysics. And hopefully today I'll show you that this one small plot is hiding a lot of information that we really are struggling to get a handle on today. Now, for the cosmologists in the room, in the next decade, the goal is to get the Hubble constant, the expansion universe, to 1% uncertainty. I don't know if that's possible. I mean, it sounds great. It's a nice target, but this is a big goal. And as Dr. Freeman and Dr. Medor have shown, it's very hard to get the Hubble constant to high precision. If you look at the Spitzer results from 2012, where the Hubble constant is at 2.8% error, we have uncertainties cropping up in many different ways. We have the 0 point, how radiant stars connecting to the host galaxies, metallicity, just fitting the PL relation, crowding, and everything creates uncertainties. And trying to understand these uncertainties is very important. And you can see going from 10% uncertainty to 2.8 uncertainty has required a tremendous amount of work in understanding each of these uncertainties. And I think from a stellar evolutionary perspective, we would like to be able to see if we can actually contribute to at least 3 of these: the 0 point, the metallicity, and the PL fitting. So we need to understand that physics in extreme detail. And of course, part of the reason we want to understand this is because of the Hubble tension, which is this great key phrase that really doesn't say anything other than we have two measurements that sort of agree and sort of disagree. And the Hubble tension arises because the Planck satellite measured a Hubble constant that is significantly smaller than we measure from local universe from Cepheids, for instance. There are ways around this. Perhaps there are more neutrinos in the universe than we know about, which would also could be one solution to Hubble tension. But it kind of drives home the fact that no matter what, we need to understand all the systematics and the physics underlying Cepheids to make sure that Cepheids aren't the problem. I like to think they're not the problem, but I can't say they're not. So to do this, we want to go from the empirical to the theoretical. From the empirical uncertainties, where we have the slope, the 0 point, and the metallicity dependence, we need to understand things like the Cepheid mass discrepancy. Like for the last 50 years, or more than 50 years now, we can't actually measure their mass properly. Different measurements give us different results, and they always disagree. Do Cepheids have strong stellar winds? Cepheids are yellow supergiants, sitting next to red giants or red supergiants, which have strong cool winds. And on the other side are blue supergiants and blue stars, which have strong hot winds. Are we sure that Cepheids don't have winds at all? Or if they have winds, what is their impact? Rotation, stellar rotation is another issue that we need to think about. Stars are born rapidly rotating, and that impacts how they evolve significantly by extending their main sequence lifetime, by changing the potential structure of the blue loops of a Cepheid, interacting with the red supergiant branch. So we need to understand that as well. While I think we have a good handle on nuclear fusion, particularly for main sequence stars, there has been discussion that the helium reaction rates are actually not well understood. And from lab experiments to the best understanding today, you can actually do very significant tests on Cepheid evolution to understand how helium fusion actually impacts evolution. And of course, then we have some of the more grand challenges, such as convection. Cepheids have convective photospheres. That seems to dictate how the red edge of the Cepheid instability strip, and probably have some interplay as you get towards the bluer side before convection is too deep. But how do we actually model that or incorporate that into our understanding? And finally, I think something that sort of we leave behind is, what's the binary rate for Cepheids? And we are pretty sure Cepheids don't have very close binaries because they're mostly almost all post-red giant branch stars. But binarity is kind of important. We see eclipsing binary Cepheids in the LMC, and we know the binary fraction in the Milky Way is approximately 40% or 50%. And so this is something we need to also consider, is how binary evolution works. So I'm going to start today with the Cepheid mass discrepancy, because I think this is kind of, from a theoretical perspective and a stellar evolution perspective, the key problem for understanding Cepheids from evolutionary physics. And this mass discrepancy is the difference between two measurements. One, you have your HR diagram, you have the luminosity and temperature, and you fit that evolutionary track and get a mass of Cepheid, your standard technique to measure masses of stars from stellar evolution tracks. The other way of doing it is from the pulsation modeling. You have, the period mean density relation tells us a lot about the structure of the star, and you can use pulsation models to measure the mass of the star. And every time, just about, the mass from evolutionary models is greater than the mass from pulsation models. And that difference can be upwards of 20 to 30%. Now, there are tricks we can use in stellar evolution modeling to try to make that work. But the issue is that we have this the mass discrepancy seems to persist, and it's not really a constant effect. So if we look at this plot, we get the mass discrepancy on the left-hand side. On the right is a prescription for convective core overshooting. This is, if you think of a main sequence star with a convective core, we treat it using mixing line theory, in which case you think the convective boundary, the eddies have to stop, and the velocity goes to zero, and the position goes to zero, or the acceleration goes to zero. But what happens is that, in reality, is that an eddy's velocity acceleration goes to zero, but it could penetrate above the convective boundary. And we call that overshooting. And when that happens, when the eddies reach above the boundary, it mixes fresh material back to the core. So it adds hydrogen to the core. It extends the main sequence lifetime of that star. it creates a more massive helium core, which means that you get a more luminous star for the same mass of star. So if we add overshooting to our models, we could sort of like scale up or scale down the amount of mass discrepancy depending on our prescription. The challenge with this is that mixed learning theory is one ad hoc theory, and convective core overshooting is ad hoc theory on top of an ad hoc theory. So we're really trying to do two wrongs to make it right. It's not ideal, but it's what we do. There is some evidence that's been suggested that the mass discrepancy is also a function of metallicity. This is based on observations from the Milky Way, LMC, and SMC by Stephen Keller in Australia. And he suggests that perhaps in the Milky Way, the mass discrepancy is about 10 to 15%. And in the SMC can be as much as 20% on average. So that's also a bit of an issue. That could be related to issues of how helium abundances change with metallicity. It could be an issue with convective efficiency. It could be an issue of rotational efficiency. All these things play a role that we have to try to address. But my favorite way to sort of actually understand this from an evolutionary perspective is to use real-time stellar evolution. This is where I think Cepheids are really cool. That these are one of the few stars that don't explode that we can actually see evolve. So, Arthur Eddington is probably the first recorded person to ever try to really do this, where he compiled the observed minus calculated diagram for the Cepheid X puppet. And this is the change in the period as a function of time, or more directly, is the change in maximum light as a function of time. So when you see the parabolic change, what you're seeing is linear period change. The period can be growing or decreasing depending on the parabolic shape. Based on an analysis of the period change, Eddington argued that that period change was solely due to stellar evolution, and therefore, based on the rate of period change, the star is evolving too slowly for its energy to be generated from contraction. So, for 1920, that's pretty cool. That's a pretty cool test. Imagine what we could do if we actually throw real stellar evolution models at this. And that's some of the research projects I've been focused on. So luckily, we have more than one star with observed period change. David Turner, now retired from St. Mary's University in Halifax, Canada, he compiled data for about 200 Cepheids in our Milky Way. And he plotted their period change as a function of their period. So the top plot is the period is increasing with time. And we correlate that to the first and third crossing and instability strip. And I'll give a brief reminder what that means presently. And then on the bottom plot is the period is decreasing with time as a function of period. And you can see there are some apparent correlations, and perhaps this says something about how we understand Cepheid evolution period change, because the solid lines are rough boundaries as determined by David. And so we could think of this first, second, third crossing based on how we view stellar evolution on track. So here is a stellar evolution track, luminosity on the left, temperature on the right, for a 5 or 6 solar mass star. You can see the line, but each line in the line there are different dots, and the dots are spaced by 100,000 years. So on the first crossing, the star is finished fusing hydrogen in the core. The core is contracting, the envelope is expanding, and that's driven by thermal timescales. So it's evolving rapidly across the HI diagram. And you can see between the two dots on the rough estimate of the boundary of the instability strip, that timescale is of order 100,000 years or less. Now the star evolves at the red giant branch and comes back down and begins the blue loop, where it is evolving blueward or to hotter temperatures in here. And you can see, it's moving relatively quickly, but it's evolving blueward to some point. And in this case, that point is in the middle of the instability strip. At some point, at this point, the star is undergoing shell fusion and some helium fusion in the core, but very little. At some point, helium fusion becomes the dominant process, and the star starts evolving redward again. And that timescale is dictated by the helium burning lifetime. And so you see, there's a lot of models in here. So it takes millions of years living on the third crossing in this case. So we have issues of relative time scale that we can compare to populations and sort of make estimates of how well we understand cell evolution. Because we know the first crossing is really quick, the second crossing not so much, and the third crossing is really long. So we could take that and compare with theory. So we have the first crossing, which appears to have, according to David Turner, the left-hand plot is based on theoretical models from Bono et al., I think, if I remember correctly, compared to the observations. And you can see there are very few stars that David Turner classifies as first crossing. That's reflective of the fact that it's just such a short time scale. And the second crossing, which is all the stars in the bottom plot, we ignore the possibility of fourth and fifth crossing. When we include things like rotation and convection core overshooting, those loops those fourth and fifth crossings or secondary loops tend to disappear. So it's not clear that those are actually real. So we tend to focus on there only being 3 crossings in the instability strip. And so that blue crossing on the bottom, you can see there's more, but there's not nearly as many as that appears to be on the third crossing. So we can take this and test our cell evolution models. We can import additional ingredients. We can talk about convection core overshooting. We can start including rotation. Rotation has the ability to mix additional material in the core through rotational mixing processes and circulation. So it can have a similar behavior as convection core overshooting, but it can also change the structure of the blue loop. And then we also want to talk about mass loss while the star is a Cepheid. This is kind of contentious because it's in this weird void where if you think of hot stars, the mechanism of driving winds in hot stars is ionized iron. That's not the case for Cepheids. On cool stars, it should be dust. That should also not be the case for Cepheids. But we have to be aware that pulsating stars have ways of ejecting mass. And so we should be, I think it's important to actually think about this issue. So I'll just remind you again how overshooting operates. So standard mixed-line theory, which goes back to engineering processes in the 1920s, which should tell you, we're not really dealing with stellar physics here, is that you have a convective cell at the base of your boundary, and it is hotter and denser than the surrounding medium, so it rises to the top. At the top of the convective boundary, mixed-line theory assumes the acceleration and velocity both go to 0. That's physically impossible. You can make the acceleration go to 0, but you can't really make the velocity go to 0. So it's believed, or we assume, that the eddy on the top will actually push a little further above the convective boundary and mix material in. And we assume we assume some sort of mixing scale that changes the size of the mass, or the mass of the core over the main sequence lifetime. So it's very ad hoc, but it seems to help with observations. And is used regularly to understand hot binaries with convective cores. And so we could see this in one test here. So this is the LMC eclipsing binary Cepheid 226. So from very precise observations of the mass and radius of both stars, it's very clear that you have very limited options of how we can fit the properties of the star. And so what I show here are underlying the 2 data points are stellar evolution tracks with different amounts of core overshooting. And the blue loops increase, luminosity loops increase with increasing overshoot. So one thing you can notice is that you get loops occur at higher luminosity than with no overshooting, but also that the blue loops tend to contract, which is actually still a big problem because it makes it very hard to fit the blue of Cepheid. But what we find is that we need to have some moderate convective core overshooting to fit this system. And it fits it really well. This has been tested by multiple groups. And we can use this overshooting to sort of fit the mass discrepancy as in this plot here, where we have the mass discrepancy on the left as a function of evolutionary mass on the x-axis. So, from evolutionary models, we might say 15 solar masses, and pulsation mass is 20% less. But if we assume some overshooting parameter, we could sort of fit all these kind of objects underlying it. However, the scatter in the mass discrepancy makes this kind of problematic. We can only go so far with using overshooting as a solution. I also think it's very important to talk about stellar winds. And this is kind of a contentious issue, and there's lots of circumstantial evidence, no pun intended. But I think probably the key issue here is this observation of Delta Cephei. It's pretty scary to have your prototype star be the odd one out. And so what we see in the Spitzer observations here, multi-wavelength, is the presence of an infrared bow shock that's consistent with the star moving through space with the wind. Now, based on this measurement by Massimo Marengo, you might suggest a mass loss rate of order 10 to the minus 8 solar masses up to 10 to the minus 7 solar masses per year. To put that in context, that's essentially the star losing about 1/10 of the Earth's mass every year. That is also much higher than you would expect for the main sequence evolution of the same star. A 4 or 5 solar mass main sequence star should lose mass at about 10 to the minus 9, 10 to the minus 8 solar masses per year. The 4 to 5 solar mass red giant or red supergiant star, probably around 10 to the minus 9. So we're talking mass loss rates that are comparable across the HR diagram for the same mass, or potentially even more. And given that Delta Cephei is a second crossing Cepheid, its evolutionary changes are slow enough that if the bow shock were primordial, the star would have already blown away from it, moved away from it. So, or the bow shock would collapse on itself. So we're pretty sure that if the bow shock is wind, it has to be in situ. Similarly, Lynn Matthews presented radio observations of Delta Cephei, and you see embedded is the infrared radiation, or infrared observations in red, and the contours is the radio nebula that she detected. Now, there are issues with the radio nebula in terms of symmetry, and that's an observational artifact, because at some velocity bands, it's contaminated, so you can only get a certain part of the nebula in the observation. But the density of material is actually consistent with the observations from infrared measurements, and potentially suggests a mass loss rate of the order of 10 to the minus 7 solar masses per year as well in radio frequencies. This is kind of troubling, but at this point has not been seen in any other infrared bow shocks or radio nebula have been really observed in any other Cepheid, with the possible exception of RS Puppis, which has a circumstellar nebula, but no obvious bow shock. So this sort of motivates the question of what's going on. We can go a little bit further and look at a little more indirect measurements, observations. Infrared interferometry, Anton Morin, Pierre Cavella, and other members of the French group and Char groups have been observing Cepheids, and they have a lot more Cepheids observed with interferometry now. And in the K-band, they find evidence for an excess flux. For comparison, so in this plot here, I have the interferometric observations for one system, but the more interesting plot is here on the right. So this is the period of the star and the infrared flux variation. And at 0, 0 is the yellow supergiant alpha per. They do not detect any sort of circumstellar flux around the yellow supergiant, but it does appear to stand out around Polaris, Delta Cephei, a little bit around L Carinae, and YO. And more modern, and they've been filling this plot out in the last decade much more with Eta Aquila and a few others, Cepheids. This infrared axis appears persistent. It's not obvious that this is a real effect or is an artifact from the analysis, but the fact that we have a yellow non-pulsating star with zero infrared axis is suggestive, to say the least. But the story gets weirder in my mind, because Nicholas Nardetto also recently did optical interferometric observation, so V band of a nearby Cepheid. case, I believe this is delta Cephei. And you can see this is the angular diameter measured from interferometry as a function of pulsation phase. So the bottom plot is in the K band angular diameter. Sorry, the top plot is the K band angular diameter. So in K band, the star is bigger, and V band underneath. The pink points refer to K band measurements, whereas the blue points are V band angular diameter direct measurements. So if you would expect with the V band, the radius to be much smaller, but there are actually phases where the V band radius is larger than the K band. This is suggestive of an actual optical shell around the star that may potentially exist, or could potentially be an artifact from changes in the pulsation dynamics. That could be an outflow as well. Could be an outflow of ionized material in the optical band. So this is raising a number of issues with understanding stellar winds in classical Cepheids. The one that kind of always throws me for the loop is classical Cepheids being X-ray variables. Now, the fun part about this here, about these plots, if we look at the right, you see the UV plots of delta Ceph in silicon and nitrogen. And then you have the XMM and Chandra X-ray fluxes. The baseline of X-ray flux is actually much smaller in luminosity than for the sun. So this is really, at quiescent phases, there's no X-ray flux. But there's a sharp phase where the flux increases by factors of 10 to 20. And as Scott Angle, for his PhD thesis, noted, that this is consistent with a plasma of upwards of 10 to 20 megakelvin. I think that the thing that catches most Cepheid people's attention here is the phase. This actually corresponds to a phase of the star reaching, the pulsating star reaching maximum radius and just beginning collapse. So this might be suggestive of, say, you have the star expanding and you have shock waves progressing, and then as the star begins to collapse, the shock waves hit the collapsing material and get completely energized. You know, this phase is possibility telling us something about the mass rate. On the other hand, the UV is telling us a completely different story. We don't see a peak in the UV at that same phase. We see the peak of the UV at a much later phase, very close to actual minimum radius, so the star is contracted to its minimum radius and is starting to expand again, or getting ready to expand, which might be suggestive, which is definitely suggestive of shock waves interacting with the photosphere. But, and you can do an adiabatic shock and actually show that you can reach those temperatures. So the story is very different and understandable. The X-rays is a lot more surprising in maybe shocks or magnetic fields or something else. The challenge with this is there have been hints of this kind of X-ray bursting behavior in other Cepheids, but we have not confirmed it in any other Cepheid. The one that was closest ended up having an X-ray companion, which was giving us all the flux. So we're having this issue of, we have a lot of, well, largely delta Ceph doing a lot of funny things as the prototype, and trying to figure out if that's a general property is a tremendous challenge. So we could put all these kind of circumstantial pieces of evidence together and perhaps build a picture of a stellar wind. And one possibility that we've postulated is that, you know, you have a pulsating variable with shocks pushing material outwards, and those shocks collide at one phase to give us the X-rays. As the shock collides to give us the X-rays, it pushes material away, sort of like swishing water in a bathtub. And at 1 AU, you start getting these cool shells that are seen in optical interferometry. And at about 10,000 AU, you start getting the Spitzer type of bow shock. And so we kind of put this together as a very speculative picture, hinting at possibilities for understanding these stars. But as a picture, we can try to do theoretical, but maybe there's another way of testing this. let's put mass loss in our stellar evolution codes and see what happens. So this is work I did in 2011 at the University of Bonn. And what we did is we computed 4 different groups of stellar evolution models. One stellar evolution model is our base set, which is no Cepheid mass loss, no special prescriptions, no overshooting. These are the vanilla models. Then we compute 3 sets that have high mass loss rates. So we're talking 10 to the minus 7, 10 to the minus 8, 10 to the minus, even 10 to the minus 6 solar mass per year in some cases. And then we scale different amounts of convective core overshooting for each group of models. I should note here that the convective core overshooting parameter I use is actually different than the one I showed before. Different codes have different parameterizations. But what we can see, for instance, if we don't use any overshooting or mass loss, we get multiple blue loops on the left here. So as you follow this 4 solar mass track in the upper left, you can see multiple blue loops intersecting here. As soon as we add mass loss and overshooting, that 4th and 5th crossing go away. The tracks change in the blue loops change in luminosity. In some cases, the blue loops are truncated, driven to the right side of the instability strip, which is actually telling us that mass loss is occurring at such a high rate that the star can't actually adapt. So basically, the star is just trying to expand and not contract when this is happening. So there's actually limits to how much mass loss a Cepheid can lose and still become a Cepheid. But what we find is that we can explain the mass discrepancy with what we would consider moderate to high.
Sorry, which panels are the different mass loss?
I'm sorry. Could you repeat that?
Yeah, you've got 4 panels and you've got mass loss equals 0 in the top left, but then the other ones have different convective overshoot, but then there's no indication of the mass loss rates in those. So I was confused. Yeah, so in the other 3 panels, the mass loss rates are all the same. They're all about 10 to the minus 7, 10 to the minus 6. They're mass dependent using a analytic shock theory, but it's all basically you get this thing that they're all high mass loss rates. Okay, sorry about that. Thank you. Thank you. No problem. Thank you for the question. And so with the high mass loss rates, we can change the instability strip and the properties of Cepheids dramatically. And with high overshooting on the lower right and high mass loss rates, we almost erase the existence of Cepheids from the HR diagram, which is not something we really want to do, but it helps provide limits. And so we see that some overshooting and some mass loss can actually solve the mass discrepancy in this respect. And so if we take the plot and actually compute the mass discrepancy, so at the bottom is the initial mass. So that's the masses as dictated by the plot in the upper right, or upper left, sorry. And then we compute how much mass we remove from and change from convective core overshooting on the lower left and the lower right. We actually can interject upwards of 15 to 20% mass discrepancy from having mass loss in this. So essentially, I guess the point I'm trying to make is that by having mass loss and overshooting, we can actually resolve that mass discrepancy to some level. And what the benefit here is having the mass loss and having the mass loss being a function of physical parameters is that the change in the mass discrepancy is not static, it's not uniform across all masses, which means we can actually essentially inject noise into the problem, which helps understanding relative to the observed Cepheid mass discrepancy, which seems to vary dramatically across different stars. Another way of testing stellar winds is to go back and look at their real-time stellar evolution. So this is for Polaris itself, work done with Scott Engel and Guinan using about 200 years worth of observations of Polaris. So some of these, so we compute the O-T diagram to measure the change in period, and it goes back to data that was taken by unaided eye. So this is highly technical instrumentation here. And as we can see, we get this beautiful parabolic shape that symbolizes a constant period change, except for one point,
which is in the early 1960s, where there may be a glitch, but we don't know if it's real. So either way, we take the data and we can compute it a conservative rate of period change from the observations, which is that small box on the lower in the right plot. So this is the period change relative to the pulsation period in per million years. So it's how much the period change will change in a million years as a function of stellar luminosity. All of the points are different stellar evolution tracks with different amounts of convective core overshooting, with no special prescription for mass loss. So the top grouping that sort of curves upward really quickly is the stars on the first crossing of the instability strip. So you can see that their rate of period change is very sensitive to the luminosity, i.e. very sensitive to the mass. And beneath the box are stars on the second and third crossing of the instability strip. It's worth noting that these are below the box. There's no agreement between models and period change at all. Of course, I should note, to do this analysis, we have to assume that Polaris is at in this case, 132 parsecs, which is the Hipparchus distance, because I'm predating a lot of the, this predates a lot of the more recent analysis. But even within the other more recent analysis, the box only shifts left and right a bit, and it would have to be, to fit the first crossing models, it would have to be at about 100 parsecs for Polaris. So what we see here is, as an issue, is if we just take this as a very linear step, that the period is driven by the mean density. So the change in the period is the change of density. And so we just say that difference between the box and the point is simply a mass loss rate. Now I'm ignoring how the mass loss rate feeds back into the evolution, but just for argument's sake, just saying that that difference is a potential mass loss rate. That sets a limit of mass loss rate to be about 10 to the minus 6 solar masses per year. Probably more than reality, but it is telling us that there's a potential for a very strong wind for this star. We repeated this analysis, but instead of doing it for star to star, we just did it for populations. When I showed you the evolutionary tracks previously, the second crossing is much quicker than the third crossing, and the first crossing is just rapid. So we can actually just compute a synthetic population and compare the number of positive stars with positive period change and the number of stars with negative period change. That makes a very good proxy for stellar evolution timescales. And so this simple ratio is something we can test. So from the Turner sample, about 2/3 of all stars, or all Cepheids in the sample, have a positive rate of period change. So they're evolving redward on the instability strip. 1/3 are on the second crossing. So we can go back to our stellar evolution models, and we can, with some type of star formation rate, a constant star formation rate, it doesn't really matter because we're drawing from the same population. Some distribution in the IMF, etc., and we can do the analysis. And what we find is that when you use models with no real overshooting or no mass loss prescription or rotation, about 85% of the models have positive period change. It's very hard to draw error bars from this because the observations, it's not clear what the biases in the measurements from the Turner sample is. So we're sort of stuck with sort of vague approximations here. But we do see that we're predicting way too many stars on the third crossing, or the time scale for the third crossing is actually much longer than it is from what we would guess from observations. So we're actually learning something about the blue lobe structure in this situation, under the ideal assumption that the first crossing is normally negligible. If we interject our stellar evolution models with a constant mass loss rate, in this case it's a constant mass loss rate of 10 to the minus 7 solar masses per year, the population distribution changes very much. And so on the second crossing, it doesn't seem to change very much, except for maybe the luminosity of the theoretical data, and that's denoted by the color bars. And I should note the colors refer to the probability distribution. So very few stars exist at a high luminosity, and most of the stars are at lower luminosity. but what we see is a significant change in the fraction. So the positive period change decreases when you inject mass loss rate. And in fact, we brought it down to about 70-30. So, which is probably more believably close to 2/3, 1/3 than 85% is. So we argue this is actually significant evidence for Cepheids in general having high mass loss rate. And something we are still considering and trying to work on. You know, as you can see with the population of the Cepheids denoted by the color and the points denoted from the observation do not overlap in any way. So doing this as a one-to-one kind of estimation is is essentially impossible. So, and to do this as a more proper analysis, we need to have independent measurements of each star's volumetric luminosity, period change, and pulsation period, and other properties. But in the end, what this means is that mass loss is probably ubiquitous in classical Cepheids. And that alone could feed back into things like the mass discrepancy, into infrared fluxes, and perhaps even into the pulsation period, therefore affecting the PL relation or Leavitt law. However, the evidence isn't perfectly clear. We did the same analysis with the massive Cepheid L Carinae that we did with Polaris with a number of years data, and we also have a very nice O minus C diagram, so we can get a very strong fit of the rate of period change. In this case, the rate of period change is fairly high, which is consistent with L Carinae being a massive star, and we could do the same test over again. However, in this case, because we have the interferometric observations with L power, we use the radius instead of the volumetric luminosity. What we see in this plot here, so period change again on the left. The first gray curve is the first crossing. The second gray curve pointing upwards is the third crossing. And L-car doesn't really agree. It's marginally consistent when you ignore mass loss. So you basically treat it as a standard star with the mass loss. It's marginally consistent. This is sort of also kind of consistent with it being close to the red edge of the instability strip. Whereas when we include mass loss in the models diverge from L-car by more than a few sigma. So if we were to use this analysis to say we measure the mass loss rate of L Carinae, we would actually say its mass loss rate is approximately 10⁻⁹, which is consistent of what you would expect for any star that is of order 10 to 13 solar masses. And so this would contradict the conclusion that mass loss is sort of ubiquitous in classical Cepheids, except for the fact that I can cheat my way out of this by saying L Carinae is a massive star, and massive stars are a small number of statistics relative to the rest of the population. So, you know, I will take my cheat. Very recently, I was working with the Harvard group, Sophia Moscio and Nancy Evans, and Sophia did a project to actually test whether or not we can get the mass loss and the X-ray flux from shock models. Sophia, I'm blanking on which MHD code it was now, took an MHD code, implanted a corona on top of the model, and put a pulsating piston beneath it. And so essentially this is the same kind of prescription we would use for a dynamic atmosphere if it's an AGB star. You have your piston beneath the photosphere, and you let piston go up down in some sort of sinusoidal way, and monitor how the atmosphere responds to it. Sophia did this with upwards of the corona or pseudochromosphere, and found that based on the analysis of a number of different possibilities, that she was able to find that the X-ray luminosity is actually consistent, at least in magnitude. The phase is somewhat arbitrary in this situation, but the magnitude and the variation is consistent with what was observed for delta Cephei. On the other hand, what she found is that the mass loss rates are low. In this case, for delta Cephei would be 10⁻⁸ solar masses per year or less. So, and the possibility is we seem to be reaching a consensus that mass loss is probably not as important as I had originally suggested, but I remain hopeful, largely because for solving, as I mentioned, for solving mass discrepancy, mass loss and convection core overshooting go a long way. And there are only so many ingredients that actually will do that job. And I will shift over to discussing rotation as another possibility right now. Rotation is an interesting challenge in stellar evolution, in the same way that convection is an interesting challenge, in that it's inherently three-dimensional, and we cheat and do it in one. So to do rotation in stellar evolution codes is we treat this as a pressure term in the code with some sort of circulation type of terms. And depending on the code, you can do this as an advective method or an integrated method. And so Richard Anderson decided to test this using the Geneva stellar evolution code and with rotational mixing for perspective Cepheids. And so you can see here for a given mass, if you increase the rotation, you increase the mass of the core due to rotational mixing, because rotation mixes material into the core during the main sequence lifetime in the exact same way or similar way as convection core overshooting. So you increase the luminosity of the stars, but you also change very significantly the shape of the blue loops. And what he found was that with higher rotation, the difference between the second and third crossing occurred at very different luminosities. So the third crossing, the star would be actually much brighter. It's unclear how true this is because observational analyses of Cepheid sort of suggest limit of about 20 kilometers per second. But being these are yellow supergiants that are highly extended, 20 kilometers per second can actually be a significant fraction of the critical velocity for some of these stars. Richard followed this up further and compared this to the mass discrepancy and suggested that some stars born with moderate rotation, so born at about 1/2 of the critical velocity of a star, would actually be sufficient to explain the mass discrepancy, which is, and this is true, if all stars are born with at least 1/2 of the critical velocity. Observations of rotational distribution suggest that actually we peak close to 0 or 0 or 50 kilometers per second, so not anywhere near moderate rotation, and decrease with higher rotation. So we have to think about the rotational distribution of stars here. And I'll skip that. And when we think about this in terms of rotation rates, so a student worked with a student, Cassandra Miller, and published this year, and she created grids of stellar evolution models with convective core overshooting, no prescription for mass loss, but at bins of 25 kilometers per second. And then she treated each rotation bin as a separate population and computed the probability and computed the period change of those models for each population and compared them to observations. So just like we did with the mass loss, looking at the 2/3 for the observation, 2/3 of stars have positive period change, 1/3 have negative. Cassandra took the models at starting from 0 kilometers per second rotation and did the analysis and found, like we did before, about 85% of stars have positive period change. Repeating this at different rotation rates and not treating them, but treating them as separate populations, which isn't ideal, but based on this plot, we don't actually have to co-add them because in every population, the theory still overestimates the number of stars with positive period change. So while rotation can be a way to sort of measure the mass discrepancy, what we see is that even at moderate rotation or high rotation, we still overestimate the number of Cepheids. So we solved one problem, but we still have the other. And so in this case, Cassandra and I argued that rotation is a sufficient argument for the mass discrepancy, but it is not sufficient for understanding Cepheids in general. So to understand period change, we still need things like mass loss and stellar winds, which feed back into the mass discrepancy. And what we end up finding in this general population is that it's not one piece of physics that's going to solve the problem, is we basically need every piece of physics, which makes this a long problem. But there are some case studies that we can do. That's kind of fun. One of my favorite is the Cepheid B19, which is one of the Cepheids in Andromeda observed by Hubble. And it is a long period Cepheid, 50 odd days, with a nice B magnitude light curve as seen by Hubble. However, in 2001, Lucas Macri kind of did the same observation of the star and found it wasn't pulsating. So, if we look at a left plot, the light curves from Hubble with high amplitude varying over magnitude. In the 60s, about half a magnitude variation, and less than 0.1 magnitude in 2001. So is this a Cepheid that didn't exist? Or is this a Cepheid that evolved? And it's possible to evolve, because if it's a massive star, that time scale can be of order 1,000 years, depending where it is on the HR diagram, or on the instability strip, I should say. And so perhaps we sort of got lucky, and we actually saw a Cepheid evolve its way from the instability strip. And so Scott Engel did a quick analysis to measure the temperature and luminosity of it. And with very big error bars, V19 appears to be pretty close to the blue edge, which could be consistent with it evolving away. So an undergrad at U of T decided to take up this challenge. And we were using a stellar evolution code that, if you make the time scale small enough, you can make it pulsate. It can compute dynamic evolution. So what we're looking at here is the stellar evolution model of a 15 solar mass star as it evolves near the blue edge of the instability strip. So you can see on the left, the time going from the starting point about 0 years to 800 years. And the luminosity, mean luminosity is relatively constant, but the temperature is increasing on the bottom. And you can see that the amplitude grows pretty quickly, stabilizes, and after about 600 years, it starts decaying. And on the right, we see this is the same plot, but on the HR diagram, variation on the HR diagram. And so you can see that as the star evolves very quickly, and over just a few hundred years, it very quickly drops from 1 magnitude to a small fraction of the magnitude. So perhaps we actually seen V19 evolve away from the instability strip in action, which I'm not sure what that means for standard candles, but if you're looking at ultra long period Cepheids to determine your analysis, you have to do it now, not 100 years from now, or you need a new sample. So just give some key results in the general case, and then I kind of take the last couple minutes, if I might, or I can stop now, depending on Josh's signal or Tony's signal, about the general case, and then I'll mention Polaris as a special case, because Polaris is a very special challenge. So from the general case, we see that X-ray and radio observations are challenging Cepheids and their understanding and their evolution. And understanding that evolution has a theoretical impact on the Leavitt law, and even potentially on supernova progenitors. L-Carene is a supernova progenitor. If we don't understand it, what does that mean for us understanding type 2P and type 2N supernova? Period change is a very powerful tool for this analysis, and we're sort of only dipping our toes in the water because we've never really done a systematic survey, with the exception of the OVA survey, and that's still kind of young for some of these stars, of doing period change analysis. So this is real-time stellar evolution, and using it is a very valuable test for understanding our evolutionary models. But this is still just the beginning. We need to think about more robust rotational models. The prescriptions of rotation between different codes disagree. So of course, we're getting different results. How do we understand mass loss, convection, maybe magnetic fields? I mean, I know we say anything we don't understand about stars, probably magnetic fields, we say that. But in this case, it actually could be true. And there's preliminary evidence for Cepheids having time-varying magnetic fields, weak fields, but they exist. But 30% of Cepheids are binary. We're starting to see pulsing binary Cepheids, which is a whole other probe of stellar evolution that when we bring together is providing very high precision tests. I showed one case There's another case in the LMC which there's a significant age discrepancy, and we showed that it has to be done by a merger product of two main sequence stars that in a triple system that became a binary. And so understanding these issues are a big deal. Do I have time to keep going, or would you like me to should I click up here?
Can you tell us about Polaris in like 2 minutes?
All right, I'll jump ahead to the basic stuff here. So here's the crucial issue with Polaris. All of our understanding of Polaris depends on its distance. And so Howard Bunn, using HST parallax, found that Polaris was 160 parsecs, which means it's a second overtone Cepheid. It's doing completely different things. And so we can, just by doing the comparison, you can sort of see that it's probably a second overtone. However, from the Gaia DR2 plus HST or astrometric information, we find that the Polaris A appears to have a mass of 3.45 plus or minus 0.75, which just upends all of our stellar evolution models. By and large, we have a radius, we have temperature, we have everything else understood about Polaris but the mass. And this is a very small mass for Polaris. Nancy Evans showed that if you just plot on the HR diagram, at 3.45 solar masses, Polaris is more luminous than a more massive star. But if you look at compared to the tracks, these stellar evolution tracks are different 5 solar mass stellar evolution tracks. And we're 0.2 dex in luminosity away from a 5 solar mass track. So the mass is much smaller than we would actually guess from its luminosity. This also yields a age discrepancy with its companion Polaris B, suggesting that Polaris B is about 2 billion years old, whereas Polaris A of that order 100 million. And when you do more detailed evolution fitting, you find that the mass discrepancy ends up being 57%. So we're just too far off to be useful. What I'll take for this is that this suggests a student worked with me to do a test with population synthesis of the age discrepancy by doing population synthesis and looking at probabilities of distributions. And so on the left, sorry to show a table, but we see essentially how old Polaris is based on this table, and it's about 60, 70 million years. And on the right is a plot of Polaris B for 1.5, 1.4 solar mass objects, and the likelihood of their age on the bottom. So the age on the bottom is in billions of years. So what we see is that there's a very tiny probability, like minuscule, like 1%, that the two stars are the same age. It's most likely that Polaris B appears to be much older than Polaris A. In the end, we have to ask the question, is Polaris A a product of two stars merging on the main sequence, which creates rejuvenation and makes it appear younger? Personally, that kind of breaks my heart, because why should the nearest Cepheid have to have such exotic physics? So there are issues of, we also have to think of rapid rotation and a merger product, but hopefully the Gaia final release will save us all and tell us and answer this question. So I'll just leave my conclusions up here and take any questions you might have.
All right, thanks, Hilding. That's really interesting stuff. We can take a few minutes for questions. Can people raise their hands if there's something they want to ask?
Alex has his hand raised.
All right, go ahead.
Hey, this was really, really cool. I have a question about sort of what's going to happen with LSST in terms of seeing Cepheids going in and out of the instability strip. Is that going to be finding these in large enough numbers that it'll sort of be useful for this type of thing?
In terms of Cepheids evolving on and off the instability strip,
or is there just
that depends. Sorry.
Or are there just like too few? Is it I have no idea about like the total number of Cepheids that you might be able to see this and the expected fraction that you might see going in and out.
I suspect it's actually a very small number. You know, we see this for V19, but that's a scale, we have 100 years worth of time domain observation. So in that case, we basically got lucky. I think for LSST, I don't really know what the time frame for a lifetime of LST is going to be, but if it's less than 100 years, you know, you probably need a few, might need a couple thousand, and maybe we'll see some of massive Cepheids. I think LSST, because it's going to be observing Cepheids fairly almost daily, every day, or most days, or fairly regularly, it actually, I think, will be a very good test bed for getting precision Curie change measurements. And then if we have Curie change measurements coming from a one source or one observational source, we can understand the systematics of that much better and do have a much stronger, stringent test of our solar evolution models.
Okay, thank you. That was helpful.
Other questions for Hilding? So Hilding, I guess I'm curious whether you think that what we need most is new developments in theory or more data. You know, you showed that there are potentially ways to resolve the various discrepancies observed now, but you're also relying heavily on just a few case studies of particularly well-observed stars.
Yeah, and it's a good question. I think we're relying on a few case studies. But the funny part of those case studies is every time we get new data for those case studies, we know less. And so the data is kind of a problem. So maybe having more data will at least reassure us that the problem is real and that we can actually start doing statistics. But we really have strong limits on our theoretical understanding, especially if we want to be able to convert a theoretical understanding from stellar evolution to standard candle. And I think, so in that situation, we really need to think about things like 3D hydrodynamic dynamic atmospheres. We need to start thinking about dynamic stellar evolution codes, you know, convective codes, and binary population synthesis as well. You know, we have no real idea what happens to, can a star become a Cepheid if it's an interacting binary on the red giant branch? And what does that do to your populations or your blending or any of them? So there's a lot of things we can really work on and try to do, and it's kind of problematic. Kip and Hahn is sort of famous for noting that the Cepheid blue loop is a microscope in everything we get wrong. And you can see this in some respects just by changing in some codes the number of shells in your stellar evolution calculation, the blue loop evolution can change. So we also need to come up with, try understanding the very boring but detailed computational limits or impacts in these codes.
Quick question. When you were showing the overshooting, the loops were starting to move to the red, especially at the shorter periods, the lower masses. And so you start depopulating the instability strip, which should show you some change in the slope of the PL relation, I would think. But also if you apply too much correction, you depopulate to the point that you solve a problem, but you no longer have Cepheids because they're just not going into the instability strip at all. So that in itself, the existence of Cepheids would suggest that it puts limits on what the overshooting can be, but it still leaves you with the problem that if you invoke it, problem or not, it may be that you could see that effect in the population of the instability strip and the slope of the PL relation at a change in slope, perhaps, towards the shorter periods. Is that a fair statement?
I think that's a good point. The trouble with seeing how much we're depopulating the instability strip is we need a reference frame to compare it to. So we need a population of, let's say, main sequence stars that would become Cepheid in the future that we compare to see that depopulation.
Well, I meant it in the sense, if they never get in there, then it's that's a pretty.
If they never get in there, then yeah, that's
you're not going to see them on the first crossing.
Yeah, and that only happens when we go pretty extreme with the overshooting. The amount of overshooting that we really need is much smaller, and so I think the numbers I use are 0.1 and 0.325, and the 0.2 is considered the nominal amount for all systems, like binary systems. The Cepheid binary showed it fits perfectly with 0.2 overshooting, so we don't really depopulate we don't completely depopulate with moderate overshooting, so we get some of the way there.
Thank you.
Okay, so I think we better wrap up. Thank you again, Hilding, for that really interesting talk. You know, have a good rest of your afternoon meeting with all the people on schedule.
Thank you.